Hi, and welcome to the 8th video in my CPU series. Okay, so in the last video we put this together, which is a ROM chip that's accessing memory. We've got that hooked up directly to this counter addressing register, and so it's cycling through the random data that I've programmed into this ROM. So this isn't the whole of our memory, because we're going to have some address decoding and some RAM chips here as well. But this is going to do for us to move on and start building some of the more interesting parts of the CPU. So the thing I'd like to make a start on next is the pipeline, which is what for me is the most interesting feature of this CPU we're going to build. So we've got our address registers designed up. We've made a start on memory, and then we have our pipeline here. Now I've always been drawing it with 4 steps, but I'll talk about that in a little while. And the one thing we haven't really touched on at all is the ALU, but I think we need more of the processor up and running before we can look at that. And the GPRs are really there just to supply data to the ALU and move stuff around. So once again, we need a little bit more in place before it's worth us spending time on that. Okay, so it's probably best if we start by thinking about clock cycles again. So if we got our main clock pulse coming in, so each one of these vertical divisions is 1 clock. And the very first element or first stage in our pipeline is going to be fetch. So if we think about the fetch stage, now what that's going to need to do is it's going to need to tell the program counter to output its address onto the bus. It's going to need to pull that value in, and then it's going to need to increment the program counter. So here we've got a fetch going on. Now there's a few other things that we're going to want the fetch unit to be able to do to basically handle the situations when we can't fetch a instruction. But let's actually think about what happens next. So if we consider the fetch unit to be stage 0 on the pipeline, and then stage 1, that instruction will be clocked into stage 1 at the next cycle, and then we go on to stage 2 and 3. So our instruction is first here, and then it's here, and then finally it's in stage 3 down here. Now the interesting thing about a pipeline is, of course, that we've got these sections of the CPU operating in parallel. So in the next cycle, we've got a different fetch going on. So this is this instruction flowing down, but then we fetch another instruction while we're doing whatever we do here, and in the next cycle that moves down, and so on and so forth. So if we've got 4 stages in our pipeline, we potentially have up to 4 separate instructions at different stages of the pipeline at any one given point in time. Now, this is obviously quite different to a more basic processor that loops through the fetching, decoding, and then the various steps needed to execute the instruction. but it does it gives us some extra complications and a few extra restrictions. Firstly, the number of stages in our pipeline is ultimately going to dictate the maximum complexity of each of our instructions. So we might find situations where we might end up needing to do specific things with multiple instructions instead of one. But where we lose there, we hopefully gain in this simple path through where we can hopefully get a much higher throughput of operations going on. But one of the important things that we need to do is we need to determine what's going to happen at each of these stages. So obviously the fetch stage, its primary headline operation is to fetch the next instruction and dispatch it into the rest of the pipeline. And then we've got stage 1, stage 2 and stage 3 in our diagram, and we need to have a think about what's going to go there. Now, one of the big problems we have to deal with a pipelined architecture is we have multiple things happening at the same time. And so we have the potential for things to clash with one another. Let's say we created an instruction that wanted to read from memory in stage 1 and write to memory in stage 2, then we would immediately run into a problem, because if we did 2 such instructions back to back, when the first instruction is here and it wants to write to memory, the second instruction would be in the stage before, and it would be attempting to read from memory, and we can't do 2 different memory operations in the same cycle. And of course, in the fetch unit, that's also wanting to read from memory, so we would potentially have 3 of our pipeline stages all attempting to access memory at once, and that can't happen. Now we could do some interesting architectural things, like there's a processor architecture called the Harvard architecture, and that has a separate address bus and memory pool for program code, so that would free us from one of these sources of contention. But I definitely favour going with a more conventional architecture where working data and code is all stored in the same memory space. So looking at the different sources of contention between resources like memory is something we need to do. We need to first and foremost avoid it wherever we can, and when we can't avoid it, we need to deal with it in some way. So the first one we're obviously going to hit is memory. So it doesn't matter what we do in the later stages of the pipeline, something's going to have to be able to access memory, and that's going to be a contention with the fetch unit. So first thing we want to do is think about where in this pipeline we're going to access memory, other than the fetch unit. Now, one of our rules for where we access things in the pipeline needs to be wherever possible, keep like with like. So if we've got a particular control line, we want to avoid handling clashing of 2 things trying to do something with it. So if we can put all the things that access that into one of the pipeline stages, then we'll make our lives an awful lot easier. Where possible, we want to put things as early in the pipeline as possible, because then we're going to run into less issues and we're going to complete what we're doing. Now, there are very good reasons why some processors have what's termed a very deep pipeline, so they might have many, many more stages than this. But this is mostly to simplify the stages and get more done. And so there are trade-offs there, and for the simple architecture that I'm designing here, the shorter the better, as long as we can actually meet our goals. So I've been thinking about how to connect all of this up for a while, and so I've got a pretty good idea of what I need to do, but I feel I do need to explain some of it. So memory is our first obvious source of contention, is the thing we should perhaps place first. And when I was thinking about this, I realised that the thing that was going to constrain where memory accesses go in the pipeline was going to be the stack. So now, if you think about accesses to memory, we're going to be reading instructions, we're going to be reading and writing from memory into registers, and we're going to be doing push and pops on registers. The push and pop is where it gets interesting. So push and pop are stack operations. So a stack is, you have a region of memory reserved as the stack. We have a stack pointer, and if I were to push a value onto the stack, it would appear there, and then we would increment the stack pointer, decrement in this case, the stack pointer, and move it down to the next location. And then when we pop, we would increment the stack pointer, as we generally stick the stack at the top of memory, and then read the value. Now, there's two different ways that you can do that. You can have the current stack pointer pointing at the most recently pushed value, or you can have it at the next empty space, and it honestly doesn't matter to us at all. What matters to us is the fact that we've got two operations. We need the memory read or write, and we've got an increment and a decrement of the stack pointer, and address registers, they can do an increment simultaneously with pushing a value out onto the bus, and then the new value is present for the next cycle, or it could be a decrement. But what we can't do is we've got no control line combination that lets us do an increment or a decrement before the access to memory is made. So what that means is that we are going to have to be able to access memory from stage 2. Okay, and we're also going to have at least one of the increment or decrement for the stack pointer accessible from there. So there we go. And in stage 1, we will need the opposite. So we will need to be able to decrement the stack pointer. We could easily do that the other way around. It doesn't really matter, but the fact that we need one operation in one stage and the other in the next is what's important here. So we've got a whole bunch of other registers, address registers, we can increment or decrement, and if we stick with the idea of going as early as possible, we may as well stick all the others in there that we're not putting elsewhere. And the only other one where we would have a cause to do anything else will be incrementing the program counter, which we want to be able to do from stage 0, the fetch. Okay, so the obvious place to add control over the address bus is going to be stage 2, but we also need to be able to assert the program counter out from stage 0. So we do have a remaining piece of contention there. And in stage 0, we're going to have to worry about when we can't access memory. And for now, I think that's the limit of what we need to talk about. We've got the issue of or we've got control lines for moving data between the address registers, for performing ALU operations, but I think it's going to be better if we discuss those later on when we've fleshed all of this out a little bit more. But initially, knowing that we're going to be doing these operations in these stages means we can start looking at what we're doing. So, for the pipeline, we're going to need a bigger boat. So I've got 4 breadboards here tied together for our 4 stages in the pipeline. Now what I will mention at this point, just to embarrass myself in the future, is at present, when I sit there and I work out where I want to allocate everything in the pipeline, I only actually have these first 3 steps of the pipeline with anything allocated to them. The third step that I've been drawing on all my, the fourth step that I've been drawing on all my diagrams is currently redundant, but I'm going to be building it as we go anyway, because that's our backstop, where if we discover that we can't complete anything in time, or we have to push something back to solve a piece of contention, then that's where we're going to put it. So this fetch, we have to output the program counter, but unfortunately right now we don't have any other memory accesses that can go in, so we can initially build the fetch unit with just assuming that the program counter is being output. We need to be able to have a control line that says that the fetch unit can't access memory, but nothing else is accessing memory, so we have no need for that control line right now. And we need to be able to increment the program counter. So here's the control line for the program counter, and right now we've got no reason to do anything other than increment it, so I'm going to wire it directly into the clock. So that's pretty simple, and it kind of gets a little bit boring here, because when you actually strip away all the other bits of functionality, there's not actually an awful lot to the fetch unit. But that's good, we like it when things are simple. The added complexity will come later. So what we are going to want is a series of LEDs to show our current instruction. Oh, I've forgotten. I had a delivery the other day. I got some of these DIP LED arrays, so you won't have to watch me plugging lots of LEDs in again. I got some, I think this is a green one, and I got some red ones as well. I'm trying to colour code what I'm using for different LED colours. So red is registers, and the main 8 bits of the instruction data as it progresses through the pipeline is our pipeline's equivalent of the instruction register, which holds the current instruction in a more simple architecture. So I think that should continue to be red. Now these are 10 segment LED arrays, so unfortunately there will be a couple of spare unused ones at the end. But I think we can all agree that that's infinitely preferable than watching me plug in 8 individual LEDs. The only concern I have with that is that it does take up an extra couple of rows in our breadboard, so I have to be careful about that. I suspect some of these are going to end up getting quite tight and we might spill over onto additional breadboards. And so we need to pull data from the memory bus over here. And I hate to say it, but that's us kind of done. This stage is going to get more complex in future, but we don't have any real reason to do that until we've fleshed out this stage here where memory is going to be accessed from. There's a feature that I'm quite interested in including in the processor for inline constants. So if you imagine memory as instructions being one after another, but it would be quite nice to be able to have a constant value as part of an instruction, which would be 8 bits in size. So occasionally we will want to read a constant in from the address of the program counter, and so the work to do that is going to need to come from the fetch unit. It's going to need to be told from something further up the pipeline that actually I've decoded the instruction and the next byte is a constant. So that's a value that's going to come from the second pipeline stage. But that's literally all we have right now. Here's our random data that's substituting for our instruction stream, and in the next video we're going to look at the ways of progressing the instruction through the pipeline stages, which is where this breadboard is going to start filling out quite a bit. But for now, thanks for watching.